The most interesting shift this week is that LLMs are starting to optimize for times how times they think, not just times what times they know. One line of work is cracking ultra-long context without the quadratic cost of full attention. Another is showing that separate RL skills can be merged into one model without the usual performance collapse. And NVIDIA is pushing decoding into a tri-mode system that trades off speed and quality far more flexibly than plain autoregression. Keep watching, because the real story is where these methods win, where they fail, and what they imply for the next generation of production models. Let's explore the first paper, Hierarchical Sparse Attention Done Right Toward Infinite Context Modeling. Hierarchical Sparse Attention Done Right Toward Infinite Context Modeling. From Tencent Hunyuan with collaborators at Shanghai Tech University, HKUST, and UC San Diego, argues that chunkwise sparse attention fails mainly because chunk selection is learned too weakly. The paper introduces high-LS attention, which factorizes attention into inter-chunk routing and intra-chunk token attention, then makes routing end-to-end trainable under the language modeling loss by using a landmark token per chunk, a Taylor linearized chunk mass surrogate, and a low-rank query calibration module. On 345 M models trained at 8K context, high-LS matches full attention perplexity at 8K and extrapolates to 4M context with ruler needle retrieval still above 90%, while outperforming prior sparse methods such as NSA, dash attention, and InfLLM v2 on exact match retrieval. Inference is also much cheaper. On a single NVIDIA H800, high-LS reaches parity around 16K context, and at 512K is 13.5 times faster in prefill and 15.7 times faster per token decode than full attention. At larger scale, the authors convert the 7B OMO 3 1025 checkpoint using only 50B continual training tokens and show stronger Longbench v1 results than the Yarn extended baseline, with an overall score of 33.2 versus 31.7. The core claim is that accurately learned sparse retrieval can preserve short context quality, while enabling ultra-long, potentially infinite context modeling without quadratic attention cost. Let's explore the second paper, MOPD Multi-Teacher on Policy Distillation for Capability Integration in LLM Post-Training. MOPD, or Multi-Teacher on Policy Distillation, is a post-training method from Peking University and Xiaomi's LLM core that integrates multiple specialized RL capabilities into one LLM without weight space merging or off-policy imitation. The pipeline is three-stage. A shared SFT checkpoint is trained first, then separate domain teachers are learned in parallel with domain-specific RL, and finally, a student is distilled on its own rollouts using token-level reverse KL against the routed teacher for each prompt. On Quen 330B-A3B, evaluated across math, instruction following, and software engineering, MOPD achieves a normalized score of 0.9373, beating Mix RL at 0.8818, Cascade RL at 0.7752, Off-Policy Fine-Tune at 0.8241, and Para-Merge Task Arithmetic at 0.8574, while closing 91% to 95% of the student-teacher headroom on each domain. The paper also shows a sample efficiency gain. MOPD reaches teacher-level plateaus on instruction following with about 25K samples and software engineering with about 30K versus roughly 150K to 180K for MixRL. On the industrial scale MIMO v2 flash model, MOPD matches or exceeds the corresponding teacher on most benchmarks, including AMI 2.5 at 94.1, HMMT 2.5 at 84.4, and 2 Telecom at 95.3. Analysis finds that policy gradient and top K distillation are comparable when teacher and student share the same origin, but replacing the teacher with the distributionally different Quen 3235B A22B causes instability and even catastrophic collapse, underscoring that same origin teachers are critical for stable integration. Let's explore the third paper, Nematron Labs Diffusion, a tri-mode language model unifying autoregressive, diffusion, and self-speculation decoding. NVIDIA's Nematron Labs Diffusion introduces a tri-mode language model that unifies autoregressive decoding, blockwise diffusion decoding, and self-speculation in one architecture trained with a joint AR plus diffusion objective. The paper's core claim is that AR and diffusion are complementary. Adding the diffusion loss preserves or slightly improves AR accuracy, while the AR loss materially improves diffusion planning and stability. On 2.5b, token continuous pre-training, the ablation pipeline rises from 54.23% average accuracy with blockwise attention to 70.28%. After adding global loss averaging, DP rank varying masking ratios, two-stage training, and AR loss. The best diffusion weight is 1 equals 0.3. The released Nemotron Labs Diffusion 8B reaches 63.61% average accuracy in instruct mode, and its diffusion mode decodes 2.57 tokens per forward pass, while its lower-attuned linear self-speculation reaches 5.99 tokens per forward. Against Qwen 3 8B, the model's AR mode is plus 0.86% better on average. Its diffusion mode is plus 0.43% better, and on speed bench with SG Lang on an NVIDIA GB200 GPU, it delivers 4 times higher throughput. A speed of light analysis shows a 7.6 times diffusion upper bound on speed bench, 76.5% above linear self-speculation's realized token per forward rate, indicating substantial remaining sampler headroom. The family scales to 3B, 8B, and 14B, extends to vision language models, and uses a 20M trajectory sampler trained with a 4-layer 3, 8, 4 hidden dimension transformer. That's a wrap on today's AI paper highlights. Thanks for watching.